Your core body temperature drops by 1 to 2 degrees Fahrenheit every night while you sleep. And that drop is not a side effect of rest. It is the mechanism that produces your deepest sleep. A 1999 study published in Nature by Crouchy and colleagues at the University of Basel found that the rate of this temperature decline is the single strongest predictor of how quickly you fall asleep and how much slow-wave sleep you produce. After age 55, that decline becomes shallower, and when it does, your deep sleep vanishes. Most people believe they sleep poorly because of stress or screens or caffeine. Those matter, but they are not the root mechanism. The root mechanism is thermal. Your body is a heat engine that runs on a 24-hour temperature cycle. During the day, your core temperature hovers around 98.6 degrees Fahrenheit. In the evening, it begins to fall, slowly, steadily, until it reaches its lowest point sometime between 3 and 5 a.m. That lowest point is called the circadian temperature nadir. And here is the critical fact most people never learn. Your deepest sleep, stage 3, slow wave sleep, only occurs during the steepest portion of that temperature decline. Not before it, not after it, during it. Campbell and Broughton demonstrated in a 1994 study that when research subjects self-selected their bedtime, they consistently chose the moment when their core temperature was at its maximum rate of decline. The body does not decide to sleep and then cool down. It cools down, and the cooling itself activates the neural circuits that initiate deep sleep. This is not a minor detail. This is the primary gating mechanism for restorative sleep. And when that temperature curve flattens, which happens progressively after age 50, your brain loses access to the deepest stages of rest. But the real question is how your brain connects body cooling to sleep, and why that connection deteriorates with age. The answer involves a cluster of neurons most doctors have never discussed with a patient. Deep inside your brain, just above where your nasal passages end, sits a region called the preoptic area of the hypothalamus. Think of it as your brain's thermostat and sleep switch fused into one structure. This is not a metaphor. These neurons literally perform both functions simultaneously. In the 1990 seconds, Dr. M. Noor Alam and colleagues at UCLA recorded individual neurons in this region and discovered something remarkable. Roughly 21% of preoptic neurons are warm sensitive. They increase their firing rate when they detect warming. And of those warm sensitive neurons, about 60% also increase their activity during non-REM deep sleep. The same cells that detect heat also initiate your deepest rest. Here is how the system works in a younger brain. As evening arrives, your suprachiasmatic nucleus, your master circadian clock, signals your body to begin releasing heat. Blood vessels in your hands and feet dilate. Warm blood flows to your skin surface. Heat radiates away from your core. Your internal temperature begins to fall. That falling temperature, combined with the warming of your skin, particularly your feet and hands, sends a signal through sensory neurons up your spinal cord, through a relay station called the lateral parabrachial nucleus, and arrives at those warm, sensitive preoptic neurons. Those neurons respond by doing two things at once. First, they suppress thermogenesis. They tell your body to stop generating heat. Second, they inhibit your arousal centers. They quiet the histamine-producing tuberomammillary nucleus. They suppress the norepinephrine-producing locus ceruleus. They silence the serotonin-producing dorsal raphe. Every major wake-promoting system in your brain gets turned down, not by a sleep pill, but by a temperature signal. Dr. Edward Harding and colleagues at Imperial College London confirmed this in 2018 using activity tagging in mice. They labelled the specific neurons that activated in response to external warmth, then reactivated those same neurons later. The result? Simultaneous initiation of NREM sleep and body cooling. The same circuit, one switch. Crouchy's 1999 study in Nature involving healthy young adults monitored with skin temperature sensors across their entire bodies showed that the degree of vasodilation in the hands and feet before bed was the single best predictor of sleep onset latency, better than melatonin timing, better than subjective sleepiness. The warmer your feet, the faster you fell asleep, because warm feet meant heat was leaving your core. But here is the part nobody mentions. This entire system depends on amplitude. The bigger the temperature drop, the stronger the sleep signal. And after age 55, that amplitude shrinks. The suprachiasmatic nucleus, your master clock, contains approximately 20,000 neurons. In a young brain, those neurons fire in tight synchrony, producing strong, high-amplitude circadian signals that drive temperature, melatonin, cortisol, and dozens of other rhythms. With age, that synchrony degrades. A 2012 study published in the Journal of Neuroscience by Feynman and colleagues at Leiden University Medical Center in the Netherlands examined the suprachiasmatic nucleus of aged mice and found clear evidence of neuronal desynchrony. The individual clock cells still oscillated, but they no longer agreed on timing. The result was a flattened output signal, lower amplitude, weaker circadian drive. In humans, this translates directly to temperature. Multiple studies have documented that older adults show a reduced amplitude in their circadian core body temperature rhythm. The nighttime nadir is not as low, the daytime peak is not as high. The difference between your highest and lowest temperature in a 24-hour period, which might be 1.5 degrees Fahrenheit at age 30, shrinks to less than 0.8 degrees by age 70. Some researchers describe the rhythm as blunted. Others say it becomes dampened. Depending on who you ask, this alone could explain much of age-related insomnia. Because remember, your preoptic sleep neurons respond to the rate and magnitude of cooling. If your temperature only drops half a degree instead of a full degree, those neurons receive a weaker signal. They fire less robustly. They suppress your arousal centers less completely, and you hover in stage 1 and stage 2 sleep. Light, fragile, easily disrupted. Instead of descending into the restorative stage 3 deep sleep, your brain requires for memory consolidation, immune function, and glymphatic waste clearance. If you have ever woken at 3 a.m., not to use the bathroom, not from a noise, just awake, alert, unable to return to sleep, this is likely what happened. Your temperature nadir arrived, the decline ended, and your brain had no thermal signal left to sustain deep sleep. You surfaced, not because something disturbed you, because the temperature floor came too early and too shallow. If this is connecting with something you have noticed in your own sleep, if you are realizing that the problem might not be stress or aging alone, subscribe now. What comes next explains how your skin itself has changed, and what that means for the thermostat in your hands and feet. That section changes everything. But none of this explains why 3 a.m. is specifically the danger zone. And the answer to that requires understanding what happens to your blood vessels when the circadian system weakens. What almost nobody talks about is what happens to the vasodilation response in your extremities as you age. Remember, the entire mechanism of core body cooling depends on your hands and feet acting as radiators. Blood vessels in your fingertips and toes contain specialized structures called arteriovenous anastomoses, direct shunts between arteries and veins that bypass capillary beds entirely. When these shunts open, hot blood floods to your skin surface. Heat escapes. Your core cools. In younger adults, this vasodilation begins 1 to 2 hours before sleep onset. The temperature of the feet can rise by 3 to 4 degrees Fahrenheit as blood flow increases. Dr. Feynman and colleagues at the Netherlands Institute for Neuroscience demonstrated in 2007 that skin warming of just 0.4 degrees Celsius, less than 1 degree Fahrenheit, applied to the proximal skin of elderly insomniacs was sufficient to significantly reduce sleep onset latency and increase slow-wave sleep depth. The older brain is starving for this signal. Even a tiny boost helps. But here is the problem. Aging blood vessels lose elasticity. The endothelial cells lining your arteries become less responsive to the nitric oxide signals that trigger dilation. A 2000 study by Pache and colleagues found that people with vasospastic disorders, conditions where blood vessels fail to dilate properly, had significantly longer sleep onset latencies than healthy controls. Their bodies could not radiate heat effectively, their temperature decline was blunted, and their sleep suffered directly as a consequence. Read that again. A vascular problem, not a brain problem, was destroying their deep sleep. Cold hands and feet at bedtime are not just uncomfortable, they are a measurable failure of the thermoregulatory sleep gate. At 3 a.m., your circadian temperature rhythm reaches its floor. In a young, healthy system, the temperature continues to hold at that nadir for 2 to 3 hours, keeping you locked in the deepest phases of sleep until the rising signal begins around 5 a.m. But in an aged system, where the amplitude is already reduced and the nadir is already shallow, that floor arrives prematurely. The temperature begins to rise too soon. Your preoptic neurons lose their cooling signal, your arousal systems reactivate, and you wake. Historians still argue whether this is a circadian output problem, weakened signals from the suprachiasmatic nucleus, or a peripheral vascular problem, reduced ability to maintain vasodilation overnight. The evidence suggests both are happening simultaneously, each worsening the other. A 2018 study published in Scientific Reports from the University of Bologna found that reduced circadian temperature amplitude was associated with accelerated biological aging markers. Not just worse sleep, accelerated aging across multiple systems. So the question becomes, if your body's thermostat is losing power and your blood vessels are losing flexibility, how do you artificially recreate the temperature signal that produces deep sleep? Step 1. Warm bath or shower, 90 to 120 minutes before bed. Water temperature between 104 and 109 degrees Fahrenheit. Duration, 10 to 15 minutes minimum. A 2019 meta-analysis by Hagayag and colleagues at the University of Texas, reviewing over 5,300 studies, found this timing and temperature window optimal for improving sleep quality, reducing sleep onset latency, and increasing slow-wave sleep. The mechanism is specific. The warm water dilates your peripheral blood vessels. When you exit the bath, that dilated vasculature rapidly dumps core heat to the environment. Your temperature plummets faster and more steeply than it would naturally, mimicking the strong circadian signal your aging clock can no longer produce alone. Step 2. Keep your bedroom between 60 and 67 degrees Fahrenheit. This is non-negotiable. The temperature differential between your warm skin and cool air is what drives continued heat loss throughout the night. If your room is 72 degrees, you are trapping heat against your body. Your core temperature cannot fall deeply enough. Dr. Christopher Winter, a neurologist and sleep specialist at Charlottesville Neurology and Sleep Medicine, has recommended this range consistently in clinical practice for over a decade. Step 3. Wear socks to bed. This sounds trivial. It is not. Croce's 1999 Nature study specifically demonstrated that warm feet accelerated sleep onset. Socks create a microclimate around your feet that paradoxically promotes vasodilation. The warmth signals your blood vessels to open, which then releases core heat. The socks warm the surface releases the depth. Step 4. Time your last meal 3 hours before sleep. Digestion raises core body temperature by 0.5 to 1 degree Fahrenheit through diet-induced thermogenesis. If you eat at 9 p.m. and try to sleep at 10 p.m., you are fighting your own digestive heat production. Your temperature cannot decline on schedule. The thermal gate stays closed. Step 5. Get 30 minutes of bright light, 10,000 lux, within 1 hour of waking. This is not about sleep directly. It is about strengthening the amplitude of your circadian temperature rhythm. Morning light exposure sets the high point of your temperature curve earlier and sharper, which means the evening decline begins on time and falls more steeply. The research is still evolving on exact dose-response curves, but multiple trials at Brigham and Women's Hospital have documented amplitude improvements with consistent morning bright light exposure in older adults. Step 6. Consider a cooling mattress pad or phase change pillow. A 2024 study by Crouchy and colleagues, pooling data from 72 subjects across 3 sleep laboratories, demonstrated that a high heat capacity cooling mattress selectively increased stage 3 slow-wave sleep by an average of 7.5 minutes per night, without altering any other sleep stage. That is a significant gain when your baseline deep sleep may only total 30 to 45 minutes. The mechanism is conductive heat loss. The mattress actively pulls heat from your back, steepening the core temperature decline during the second half of the night when deep sleep is most vulnerable. If even one of these steps was new to you, hit like. It tells the algorithm to show this to more people whose deep sleep is disappearing and who have never been told why. Here is what I want you to understand about 3 a.m. It is not a random hour. It is a thermal boundary. It is the moment your body reaches its coldest point and either sustains that cold long enough to keep you in deep sleep or loses the signal and releases you into wakefulness. For decades, sleep science focused on neurotransmitters, melatonin, GABA, serotonin. Those matter. But beneath all of them, older, more fundamental, shared across every mammal that has ever existed, is temperature. Before there were pills, before there were supplements, there was a body that cooled itself into sleep every single night for millions of years. That is the system that is weakening. The good news is that it is not broken. It is dampened. And everything that strengthens a signal can be reapplied from the outside. I want to hear from you. Drop a comment. What time do you typically wake and find yourself unable to fall back asleep? I suspect most of you will say somewhere between 2 and 4 a.m. That is your thermal floor, and now you know what it means. I'd bet most of you have tried melatonin, tried tried white noise, tried breathing exercises, and none of it worked consistently because none of it addressed temperature. Your body does not forget how to sleep deeply. It forgets how to cool. Share this with someone who wakes at 3 a.m. and blames it on age. They deserve to know there is a mechanism and a solution. And if you have not subscribed yet, do it now. What I am building for next week goes even deeper into what your circadian system is doing to your hormones between midnight and dawn. It is the other half of this story. The cold is not your enemy. It is your oldest sleeping pill.